Hi everybody, it's Mohammed. In this video, I'll introduce electrons on superfluid helium as a quantum computation architecture. First, allow me to describe the architecture in words. It is based on image potential bound electronic surface states outside liquid helium. That's a fairly long description, and I think that's because this is a fairly specific physical situation, but it's also fairly quite interesting. First, image potentials. When I hear image potentials, I think of the problem of a charge outside a conducting surface. However, the method of images can be used to solve just about any problem in electrostatics, especially those where we don't know where all the charges are localized beforehand, such as when you have conductors or dielectrics. Our specific problem here is if an electron in vacuum outside dielectric surface of practically infinite extent. Our dielectric here is helium. It's a fairly simple problem. Imposing the boundary conditions for the displacement field and the electric field, one could find that the exterior solution is the same as the one with an induced image charge at the image distance of a magnitude that's less than the electronic charge. It's not quite the same because this is not a conductor, not all charges are free to move. However, if you take epsilon, the relative permittivity to infinity, you'll get the conductor result as a limit. Now this induced charge gives rise to an effective potential which is coulombic except for a factor of 4. This factor of 4 is there because the induced charge, the position of the induced charge depends on the position of the electron. So it's a bit weaker than the Coulomb interaction. Now, for a bit of history, the first to suggest the existence of those states was Shockley in 1939. He, however, did not elaborate on their properties or how they came about. It took 30 years for someone to actually theoretically demonstrate the possibility of their existence, and that was Cole and Cohen of Bell Labs. What they did was that they considered a simple Hamiltonian for those electrons with an interaction potential that is the image potential far away from the helium surface and near the helium surface at distances that are on the order of interatomic distances. This is what this number A is. The potential would be constant. This is the region where they assumed the macroscopic approximations fail. There's actually no reason, to my understanding, why it has to be constant. Maybe this is some sort of average. However, this all hinges on the fact that V0, which is the potential at the helium surface, is larger than 0. It's actually larger than the vacuum energy. Meaning, the electron actually requires energy to be injected into the helium liquid. So you have this barrier, in the case of helium anyway, is caused by an exclusion principle, basically. The electron is repelled by helium atoms due to Pauli's exclusion principle. And so you have repulsion from one side and attraction from another side, so you expect downstates to be in the middle. Now, this Hamiltonian is obviously separable, so parallel to the surface, you'll have plane waves, basically free electrons in 2 dimensions, which is interesting in its own right. Now, if you make some assumptions about the barrier, like it's really high, there is essentially 0 possibility that the electron will be at the surface of the helium, then you basically have a one-dimensional hydrogen atom. And it has a hydrogenic spectrum, which goes as 1 over n squared, and that is very attractive for a computation scheme because that is very addressable. Now, 5 years later, those states were experimentally probed by colleagues of Cohen and Cole, and they found those states to exist. But there were some discrepancies, like 5%. The transition frequencies were off by 5% or so, and they attributed those discrepancies to the interaction potential model. They actually suggested what they thought was a better one. Now, years later, we know that the reason that model fails to 5% anyway, which is impressive, is because the density of the liquid helium doesn't drop to zero instantly. It does so over a spread. Now, for quantum computing, it actually took 30 years for someone to propose to use surface electrons in a quantum computing scheme. That was Platzman and Dykman. The quantum bit in their proposal was the spatial part of the wave function, to have the 0 bit be the ground state and the 1 bit be the first excited state. Now, to make sure that there aren't many electrons in higher states, you have to have the system be really, really cold, like at 10 millikelvin. Now, how you would actually put those electrons is you basically put the helium in a capacitor and put a voltage across the capacitor and wait for electrons to wait, not long, but you'd wait for electrons to tunnel through. Now, if you have it at that temperature, the proposal actually, they claim that the proposal provides a relaxation time on the order of 10 to the minus 5 seconds. Now, the relaxation, given the voltage difference and given which Stark shifts all the states, and given how cold it is, basically the only relaxation mechanism is through coupling with ripplons. And what ripplons are, they're basically phonons except in liquid. And if I'm understanding correctly, they describe them as height variations in the helium due to thermal excitations. Basically, you have an electron in an excited state, and it transitions to a lower state by giving energy to the liquid helium, causing a ripple. Now, one obvious upgrade of this scheme is to quantize motion parallel to the liquid helium as well, by having electrodes beneath the helium surface, basically confining the electrons in 3 dimensions. Now, ripplon coupling can be further suppressed by applying a strong magnetic field perpendicular to the helium surface. I'm not sure how that works out exactly, but that's what Platzman and Dykman claimed. Looking at it classically, it sort of makes sense. If the electron has any tendency to go lower, to go near the surface, and you have a strong magnetic field, it will pick up momentum in a perpendicular direction and thus be confined to a length that you can find by dimensional analysis. However, they did provide a more rigorous derivation, by Hamiltonian and such. Now, doing all of that allows coherence times on the order of 0.1 milliseconds, and that allows for 100,000 operations in one go, which is quite impressive. Now, for the readout, what happens is you get the same capacitor that put all the electrons on the helium, and you reverse the voltage, basically attracting the electrons. But you reverse it just enough to attract the ones in the excited states and not in the ground state. And that way you can actually take an image of your system by having an imaging channel plate between the 2 electrodes, or the 2 plates, sorry. Now, another approach is to choose the qubit to be the spin of the surface electron, and that was suggested by Lyon in 2006 in Princeton. Now, his proposal is based on the entanglement of 2 spins of the spins of 2 electrons that are adjacent to each other, and electrons can be made adjacent to each other via the electrode array scheme. And what he's suggesting is to entangle them via dipole-dipole interaction, which is quite weak, which is why the operation time is fairly long. It's on the order of milliseconds. He, however, says that is not a problem, as the coherence time is on the order of 100 seconds. That's fairly impressive, but no one has followed up on that, which makes me think that there's a problem in the model, like implementing this model, but I'm not sure. Now, for the state of the art, it seems to me that current research in this architecture has gone towards utilizing the electrons for communication and memory as opposed to computation. This is mainly due to the fact that those electrons have high mobility as opposed to any other system, like a solid-state system or condensed matter in general. In 2011, they were Bradbury and his colleagues were able to efficiently transfer electron packets over helium. By electron packets, I mean on the order of like tens of electrons, like not tens of billions. And they claimed that it was error-free, which is very impressive. And quite recently, Takeda and Lyon were able to isolate electron packets above helium to one or two electrons, which is again really impressive. They, however, did not measure coherence times, so you could like moving and isolating those electrons at the expense of their coherence is not good. However, that maybe we have to wait on that. Further, there seems to be a general trend towards using this architecture in a hybrid scheme, as opposed to using it for its own sake, especially with architectures based on superconductors. Now, for comparison with other architectures, one thing that is obviously attractive about this architecture is that it's immediately scalable. All you have to do is just spread your liquid helium over a large enough electrode array, and there you have as many qubits as you want. As opposed to NV centers, where you have to identify the NV center, study its properties, because every NV center is different from every other NV center. And secondly, electrons on here on helium are quite isolated from the outside world, which was why people were interested in them in the first place. So many sources of decoherence are eliminated. However, for some reason, people aren't too excited about them, which makes me think that even though there aren't many sources of decoherence, it's not so easy to control them, maybe. Now, an obviously unfortunate aspect of this architecture is that it can't be implemented at room temperature. It has to be implemented at very, very cold temperatures, which makes commercial feasibility for commercial manufacturing harder to grasp, and maybe is why no one's too excited about this compared to NV centers in Diamond or Josephson junctions. Concluding remarks, it seems that, at least relatively, there's not much excitement over this architecture, just based on the citation count. Or maybe there is excitement, but it's just building up. I honestly did not see many proof of principle papers, like showing, Rabi oscillations or actual computations being made. It's either too new or not too exciting. Anyhow, thank you for watching.